Neptune's auroras were not supposed to be where scientists found them. For over 3 decades, ever since a single spacecraft brushed past this planet in 1989 and caught a strange, unexplained flicker of ultraviolet light, astronomers pointed telescope after telescope at exactly the place they expected that glow to be. The planet's poles, the same place every aurora in the solar system had ever been found. Nothing. Year after year, decade after decade, nothing but silence and blue haze. Neptune became the last of the 4 giant planets in our solar system, still hiding this one basic, fundamental secret. The only one whose auroras had never actually been seen, confirmed, or photographed. And then, in 2023, the James Webb Space Telescope quietly pointed its instruments at Neptune, and what came back did not just solve the mystery. It revealed that scientists had been looking in the wrong place for the wrong reason for over 30 years, and that Neptune itself had changed dramatically in ways nobody had predicted in the decades since we last got a close look. This is the real story of how Webb finally caught Neptune's hidden light, why it was hiding in a place nobody expected, and what that discovery is now telling us about a planet that keeps refusing to behave the way we think it should. To understand why this took so long and why it matters so much now, you first have to understand just how little we actually know about Neptune compared to almost anywhere else in our solar system. Neptune sits nearly 3 billion miles from the Sun, the outermost of the 8 planets, so distant that sunlight reaching its clouds is roughly 900 times fainter than what reaches Earth. In the entire history of human spaceflight, exactly 1 spacecraft has ever visited it. Voyager 2, launched in 1977, made its one and only close pass on August 25, 1989, screaming past the planet at a distance of less than 5,000 kilometers above its cloud tops, before continuing on into the dark, never to return. Everything humanity learned about Neptune up close, its rings, its storms, its strange collection of moons, its bizarre and lopsided magnetic field, came from that single flyby, compressed into a matter of hours. There has been no return mission in the 37 years since. No orbiter, no lander. Just that one brief, irreplaceable visit, followed by decades of astronomers doing their best with distant telescopes to keep watching a planet none of them could actually get close to again. During that 1989 flyby, Voyager 2's instruments picked up something tantalizing. Faint ultraviolet emissions and signatures that looked, at least in outline, like they might be evidence of auroral activity. The same kind of glowing atmospheric light show that dances around Earth's poles as the northern and southern lights. Auroras happen when energetic charged particles, usually streaming outward from the Sun, get funneled down a planet's magnetic field lines and slam into the upper atmosphere, exciting gas molecules and making them glow. Scientists had already confirmed unmistakable auroras on Jupiter, on Saturn, and eventually on Uranus as well. Neptune, by every reasonable expectation, should have had them too. But what Voyager 2 recorded in 1989 was messy, faint, and inconclusive. Nothing like the clean, sharply defined auroral ovals wrapped neatly around the poles of the other giant planets. It was enough to suggest something might be happening. It was nowhere near enough to prove it, or to actually see what it looked like. For the next 3 decades, this became one of the quieter, more stubborn unsolved mysteries in planetary science. Astronomers using the best ground-based telescopes available kept training their instruments on Neptune's poles, exactly where Jupiter's, Saturn's, and Uranus's auroras had always appeared, looking for the same kind of signature, a molecule called the trihydrogen cation, written as H3+, which forms specifically in the presence of auroral activity and glows faintly in infrared light. On the other giant planets, that molecule had been the reliable, unmistakable fingerprint proving an aurora was there. On Neptune, search after search, year after year, came back empty. Neptune, remarkably, became the missing piece of the puzzle, the one giant planet in our solar system where astronomers simply could not confirm what should have been an obvious expected phenomenon. Then, in June of 2023, a team of scientists, led by Dr. Henrik Mellon, working at the time at the University of Leicester, pointed the James Webb Space Telescope at Neptune using its near-infrared spectrograph, an instrument sensitive enough to detect exactly the kind of faint infrared glow that had eluded every previous telescope. And this time, finally, unmistakably, they found it. Buried in Webb's data was an extremely prominent emission line, the clear spectral signature of H3+, the same molecular fingerprint that had confirmed auroras on every other giant planet in our solar system. Mellon later described the moment plainly, saying that actually imaging the auroral activity on Neptune turned out to be possible only because of Webb's near-infrared sensitivity, and that seeing not just the auroras themselves, but the detail and clarity of the signature genuinely shocked him. After more than 30 years of searching, using instruments Voyager 2's own scientists in 1989 could not have dreamed of, Neptune's long-hidden light had finally been caught. But here's where the story takes its first genuinely strange turn, the part that made this discovery so much more than just filling in a missing checkbox. When the team finally mapped out exactly where on Neptune this auroral glow was actually located, it was not where anyone expected. On Earth, auroras dance around the north and south poles. On Jupiter and Saturn, the same is true. Tight, well-defined ovals wrapped neatly around each planet's rotational axis. On Neptune, the glow showed up nowhere near the poles at all. Instead, it appeared at the planet's geographic mid-latitudes, roughly the same relative position on Neptune's globe as South America sits on Earth's. For anyone used to thinking of auroras as strictly a polar phenomenon, this should sound genuinely bizarre, because it is. The explanation, it turns out, traces directly back to something Voyager 2 discovered during that same brief 1989 flyby, and which scientists have spent decades trying to fully understand. Neptune's magnetic field is not neatly aligned with its rotational axis the way Earth's roughly is. It is tilted by a staggering 47 degrees off-center, and offset from the planet's core as well, making it one of the most lopsided, chaotic planetary magnetic fields ever measured anywhere in the solar system. Because auroras form specifically where a planet's magnetic field lines converge and funnel particles down into the atmosphere, and because Neptune's magnetic field is aimed so dramatically, off-kilter from its spin axis, its auroras simply do not form where poles usually are. They form wherever those tilted, twisted magnetic field lines actually happen to converge, which turns out to be nowhere close to the planet's geographic top or bottom at all. Neptune's northern lights, in a very real sense, are not northern at all. That alone would have been a remarkable enough discovery on its own. But buried in that same set of Webb observations was a second finding, one the team was not even specifically looking for, and one that Meline himself described as genuinely astonishing. Alongside the auroral image itself, Webb's spectrograph allowed the team to precisely measure the temperature of the very top of Neptune's atmosphere, the ionosphere, for the first time since Voyager 2's flyby 34 years earlier. What they found stopped them cold. Neptune's upper atmosphere had cooled by several hundred degrees since 1989. Not a small drift, not a subtle shift within the margin of error. The temperature measured in 2023 was just over half of what Voyager 2 had recorded more than 3 decades earlier. Mellon put it directly, saying he was astonished that Neptune's upper atmosphere had cooled by hundreds of degrees, a genuinely dramatic, unexplained shift in the state of an entire planet's outer envelope. And that temperature drop, it turns out, is almost certainly the real reason Neptune's auroras evaded detection for 30 years in the first place. Auroral brightness depends directly on the temperature and density of the gas being excited. Every prediction astronomers had made about how bright Neptune's auroras should be, and therefore how easy they should be to detect from Earth, had been built using the temperature Voyager. 2 measured back in 1989. Nobody accounted for the possibility that Neptune's upper atmosphere might dramatically cool over the following decades, because nobody had any way to check, no spacecraft, no instrument sensitive enough, until Webb came along. A substantially colder atmosphere produces a substantially fainter aurora, faint enough, it now appears, to have simply been sitting below the detection threshold of every telescope and every observing campaign for over 3 decades. Neptune's auroras were never truly hidden by their location alone. They were hidden because the entire planet had quietly, dramatically changed since the last time anyone got a close look, and nobody knew it. This detail matters enormously, and it deserves to be stated plainly rather than glossed over for the sake of drama, because it reframes what this discovery actually represents. This is not simply a story about a telescope finally being good enough to spot something that was always sitting there in plain sight, waiting. It is a story about an entire planet's upper atmosphere undergoing a genuinely dramatic transformation over the past 3.5 decades. A transformation nobody was watching happen in real time, because nobody had the tools to watch it. Neptune sits more than 30 times farther from the Sun than Earth does, and conventional wisdom long assumed a planet that distant, that cold, that isolated, should be relatively stable, slow to change, insulated from the kind of dynamic swings we associate with planets closer to the Sun. The fact that its upper atmosphere cooled by hundreds of degrees within a single human lifetime suggests something far more active and far less understood is happening out there than anyone previously assumed. Heidi Hamel, a Webb interdisciplinary scientist who has studied Neptune for decades and helped lead the observation program that captured this data, explained just how long this specific piece of the puzzle had been missing. H3+, she noted, had been a clear signifier on all the other gas giants, Jupiter, Saturn, and Uranus, of auroral activity, and scientists had expected to eventually find the same thing on Neptune using the best ground-based facilities available over the years. It simply never came. Only with an instrument as sensitive as Webb, she said, did that confirmation finally arrive. Lee Fletcher of the University of Leicester, a co-author on the study, framed the achievement within an even bigger picture, noting that as scientists look ahead and dream of future dedicated missions to Uranus and Neptune, this discovery has shown exactly how essential infrared instrumentation will be to understanding these ice giants properly, calling Webb's observation the moment that finally opened the window onto the last previously hidden ionosphere among the solar system's giant planets. It is worth pausing here to appreciate the layered irony sitting at the center of this entire story. Neptune's auroras are not glowing in some remote, unexplored corner of the solar system nobody thought to check. They are glowing on one of the most photographed, most iconic planets in our night sky, a planet humans have known about and studied since 1846, a planet Voyager 2 flew directly past and photographed in exquisite detail. And yet, an entire visible phenomenon dancing in Neptune's atmosphere this whole time, sat completely undetected for over 3 decades, hidden not by distance or darkness, but by a combination of an extraordinarily tilted magnetic field, pointing scientists toward the wrong location and a slow, dramatic atmospheric cooling nobody had any way of tracking. Sometimes, the biggest gaps in our knowledge are not hiding in the places we haven't looked. They are hiding in plain sight, in the places we have looked for decades, simply because we were looking with the wrong assumptions or the wrong tools, or both at once. What happens next may end up being just as interesting as the discovery itself. Having finally confirmed that Neptune's auroras exist, having pinpointed exactly where they appear and roughly why they had gone undetected for so long, the team behind this discovery now wants to do something no one has ever been able to do for this planet before: watch it change over time. Neptune, like every planet in our solar system, is influenced by the sun's roughly 11-year solar cycle, the periodic rise and fall in solar activity driven by the sun's own shifting magnetic field. Astronomers now hope to use Webb to study Neptune's auroras and its upper atmosphere across a full solar cycle, tracking how that mid-latitude glow brightens, dims, and shifts as solar activity waxes and wanes across more than a decade of continuous observation. Nothing like that has ever been attempted for Neptune before, largely because nobody had a way to reliably see the auroras at all until now. If it works, it could finally start to explain not just where Neptune's magnetic field points, but why it is tilted so dramatically in the first place, a question that has sat unanswered since Voyager 2 first measured that bizarre 47-degree offset back in 1989. There is something quietly humbling in all of this, a reminder of just how much remains genuinely unknown even about planets we have studied for nearly 2 centuries with our own eyes. Jupiter, Saturn, and Uranus all had their auroras confirmed years, even decades, before Neptune, not because Neptune's aurora is any less real or any less active, but because it happened to be hiding behind 2 separate compounding strokes of bad luck: a magnetic field tilted at almost the worst possible angle for easy detection, and an atmosphere that quietly cooled by hundreds of degrees in the decades nobody was watching closely enough to notice. It took a space telescope built to peer at galaxies billions of light years away, pointed instead at a planet in our own solar system's backyard, to finally catch what had been glowing there the entire time. Neptune remains, even now, the most distant and least explored planet in our solar system, visited exactly once, briefly, by a single spacecraft that will never return. Nearly everything we have learned about it since that flyby has come not from getting closer, but from building better and better ways of looking from far away. This discovery is the clearest proof yet of just how much that kind of patient, distant observation can still reveal: an entire glowing phenomenon, hiding in the wrong place, for the wrong reason, for over 30 years, finally caught the moment we finally had a tool sharp enough to see it. If this story surprised you even a little, hit subscribe, because Neptune is still changing out there right now, and we are only just beginning to watch it happen.